This is AP2, chapter 24, 25, 26 review. Reflection, light, and refraction. So from chapter 24, you need to know about electromagnetic radiation. You need to know the order of the frequencies. Remember, we did that worksheet A. So you know that radio waves have the lowest frequency, gamma rays have the highest frequencies, and that therefore they have more energy, right? The higher the frequency, the higher the energy, and then obviously the wavelength goes backwards. So you should have a general idea of the order that the EM radiation goes in. You need to know it's created by moving charges. We know that a vibrating charged particle creates a magnetic field, and therefore we have an EM wave. It's transverse. It doesn't need a medium. It's fastest in a vacuum and slowest in a solid, and c, which is the speed of light, is always 3 times 10 to the 8th meters per second. So for polarization, you need to realize that it vibrates in only one plane. That one is reflected. It's reflected so that it's parallel surface. This picture's down there at the bottom is hard to see. So if you have a line, and that represents my surface, and the light comes in and it bounces off like this, it's going to be polarized parallel to the surface in this direction. If you have non-polarized light going through a polarizing filter, right, then you're going to end up, if this is S, out comes half of S, because half of it will be vibrating one direction no matter which way the polarization axis is. If it's already polarized, if I have light coming in and it's polarized maybe in this direction and it's S, and then we have a polarizer that's, that's a different direction. I know it doesn't look, it's 3D, you can't tell. But since it's not going in the same direction, now what comes out is going to be S cosine squared theta, right? Does that make sense? So if you have two polarizers, and they're in the same direction, then all of the light is going to go through. And if they're at 90 degrees, then none of the light goes through. So that should make sense, right? I think we've got that. That's not a hard concept. For mirrors, we know that the angle of reflection is equal to the angle of incidence. It doesn't matter if it's a curved mirror or a flat mirror. We just know that it always reflects. And that is always based from the normal, right? So we're looking from this line, it's this angle is equal to that angle. Even though if you have a flat surface, the other angles would be equal. Like I know these green angles, oops, that's supposed to be green. We know these green angles are equal, but those are not the ones that we're talking about. We're talking about these red ones. This is the ones that are the important ones. But you should know your basic geometry. So if you see things bouncing around, right, it's, going from one place to another, and it bounces and bounces and bounces. If you know that angle, you should be able to know that angle, and so yada, 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 and know this angle and this angle just based on your basic triangles, right? But I think most of you are pretty comfortable with that. Things to remember, just as in theory for our mirrors, is like a summary table of mirrors and lenses, since we know both of them now. For plane mirrors, it's always virtual, and M is always equal to +1 because it's always going to be upright. Right, so that's plane mirrors. Those are the easy ones. And then the convex mirror or concave lens. So a convex mirror, right, my mirror would be like this, and the light would bounce off like that for a convex mirror. And a concave lens would look like that, right? And so then when the light comes in, it diverges out like that, right? It's always virtual, and the M is always less than 1. But notice they're positive, right? These are both positive because these can only make virtual images. But when we're dealing with a concave mirror, right? So a concave mirror would be going like this, and the light comes in and bounces down, right? Or we have a convex lens, right? Goes like this, and it bends it down, right? So in both cases, it's converging the light, right? It can be real or virtual, and the M varies depending where it is. So remember, we did that little summary table in the notes about what happens. So if DO is greater than 2F, right? So if this is my vertex right here of this could be either my lens or it could be my mirror. It doesn't matter which one it is. And this is F, and this is C. If the object, right, for this one right here, if the object is over here, right, it's going to be the absolute value of m is going to be less than 1. It's going to be tiny, right? It's demagnified, and it's going to be real. So the m is actually going to be negative. As I said, the absolute value is going to be less than 1. If we get rid of this guy here, and we go to the next one, and so for this one, when we have do is equal to 2f, that means it's equal to c, right? So that means that my object is going to be right here, right? So when my object is here, my magnification is exactly -1 because it's going to be a real image. If I go down further and now I put my object here, right, so it's between the center and the focus, so it's less than 2f and it's greater than f, then the m is greater, the absolute value of m is greater than 1, so now it's getting bigger, right, we're magnified and it's real. If you stick it at f, right, you get no image, right, so if you're directly at f, this is getting really messy. So you guys can actually read it here. So if it's exactly at f, right, if it's exactly at f, then there's no image. That's pretty easy to understand. And then if it's in between, like it's smaller than if it's between the focus and the lens, so it's right here, right, then we're going to get a virtual image, and so m is going to be greater than 1 because now it gets big, right? So the idea is as you move this way, the image gets bigger, right? As you move that way until you get to f, the di moves that way, right? It moves away, gets further and further away as we go, right? Okay, so here's that one that we did before, right? We have demagnified and real, right? It's in this general area for mirrors and lenses. So it could be a concave mirror, as I've shown there, but it could also be for a convex lens, so it doesn't matter which one is, they're the same thing. But if it sees the same size, no image, and then it gets demagnified and gets bigger and bigger as we get closer to the mirror, closer to the lens. Convex mirrors and concave lenses is always demagnified, is always virtual, and it's always a virtual image. Always, 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 always. The equations you need to know for mirrors and lenses are the same as C is equal to R is equal to 2F, 1 over DO plus 1 over DI equals 1 over F, and M equals hi-ho, which is equal to negative DI over DO. Just remember that negative is important, right? You have to pay attention to where the So when you're using the equation, make sure you pay attention to whether it's negative or not, because it can mess it up. And sometimes it doesn't tell you it's negative. It just tells you it's a virtual image, or it tells you it's a convex mirror or a concave lens, and then you have to know that DI is negative when you plug it in the equation, because otherwise you get the wrong answer. Conventions to remember when things are positive and negative. DO for everything we're going to do is always going to be positive. DI, it's positive if it's real. It's negative if it's virtual. F is positive if it's concave. Oh, we got to be careful. So this is a concave mirror. I thought I fixed all these, but I didn't fix it on this one. So that's a concave mirror or a convex lens, right? And then for the other one, right, this guy, this is a convex mirror or a concave lens. So you don't want to mix those up. But so if it's positive, a positive focal, it would be a mirror like that where the light's bouncing like this, or it'd be a convex lens. Or if it was a mirror, this one for the negative one, it would be the mirrors where the light comes in like this, and then it's a concave lens. If it's a real image, and then magnification, it's virtual, it's positive, and real, it's negative, because it's upside down or right side up. So that can get a little confusing, because notice here, real is on this side and real is on that side. But if you think about it, it makes sense, because the negative just means it's upside down. Real image means it's real light, the lines really cross, it's inverted, it can focus it on the screen, and only concave, see here we have it right, concave mirrors and convex lenses can do that. For a virtual image, it's not real light, lines don't cross, it's direct, all mirrors and lenses can make them, so it doesn't matter which kind it is. Yeah. For ray diagrams, you just have to remember the 3 rules: parallel focus, focus parallel, center straight. Okay, so let's do some practice ray diagrams. So we see we have the center is listed right there. The focus is halfway through. And let's put the object, the easy one, let's put the object somewhere past the focus. So there's my object, which of course I labeled. So now we're going to draw in the arrows. So my first one goes parallel, I'm not using a ruler because I don't have a way to do that on this. And then it goes through the focus. You should use a ruler on the test. And then it goes through the focus and comes out parallel. And then the last one goes through the center, infinite long mirror, and comes back, right? And so we can see that it kind of crosses right around here. So of course I would label my image. So make sure when you're doing this that you mark your object, your image, you show your focal length and your center, and you show your arrowheads on everything, right? That's what I'm looking for. Okay, so now let's erase this and let's move that object. Let's move that object further in. So we're going to come back over here, and we're going to put the focus in, and now we're going to put the object in front of the focus. So there's my object, which I've labeled, and now let's do my arrow. So we have parallel, arrow, focus, and then we have as if it's coming from the focus. So I'm looking down here where the focus is, and it's lined up with that as best I can, arrowhead, and parallel as best I can. And then the last one goes through the center, right? It lines up with the center, and it bounces right back through the center, right? So then I need to extend them backwards. Since it didn't work, I'll do that, dash that back. So we have this one that came out through the mirror. We have this one, and this one that I need to extend back, right? So then I extend that center one back, and then, because sometimes it gets confusing of which one, right? So this is the one that I'm extending back. So I extend this one back, right? And I can see that my image is right about there, and then that would be a negative DI. So I always show my I, my O, my F, along with my arrowheads, yeah? All right, so now let's do the third one, which would be a convex. So those are all concave lenses. So let's do a convex lens. So now we're going to put the object, well, we got to put the focus in again, right? Because the focus goes right there. And we're going to put the object over here. I don't care where, just going to put it over here. And now we're going to do our rays. So we have parallel, hits the mirror, looks like it comes from this focus down here. So I line it up, and it comes out like that, and then I aim for that focus this time, so I aim for the focus, and then it comes out parallel, and then the next time I'm going to aim for the center, kind of goes to the middle right there, hits the mirror, and comes back. I see that they don't all fit, or they don't all cross, they diverge, so I see those three rays going in that direction. So now I'm going to extend them backwards. So this one came from the focus, so it should be coming from the focus. This one went through the center, so it should be coming to the center. This one's going parallel, so it should be coming out parallel. Sorry, this machine doesn't like to dash lines much. And then we come over here, and there's my image. Again, I've labeled focus, image, object, arrows on everything. Yes, I've labeled my center. Everything's labeled, right? That's what's important, right? So that's pretty much it for mirrors. Now what lenses? So here we have a couple lenses, a little on the tiny side, but I think we can do this. And so we have focus 1 and focus 2 for both of them. Let's start with our convex lens, the first one up here on the left. So we're going to have the ray of light come in, and then it crosses through focus 2. And then this one, we only put arrowheads once, right, because it's just going through. This one goes through focus 1, hits the mirror, comes out parallel, goes to the center of the lens, hits right there. And so we can see that the image, it should be ending, sorry, this is not, it's tiny. It should end right on the optical axis and be pointing down. So I'd label that image, I'd label that object, and I'm done. That's a real image. Now let's try the next one. So this time we go parallel, and it comes out through focus 2. It aims for focus 1, which is back there, so it goes up, and then it comes out parallel, and then we go through the center of the lens, because we always go through the center of the lens. That one never changes. We see that they don't match. I think I'll use a different color because I can't dash well. So we're just going to pull that one back. We're going to pull that one back. We're going to pull that one back. And so then you can see that the image is right there. So remember, it's always the ones that go through or the ones that we're extending back, just like with the mirrors. So here's my image, here's my object, and I've labeled focus 1, and I've labeled focus 2. Right, so I've got both of those foci. Now we've got the last one. So this is my concave one. So I still need to label F1 and F2, but remember now this one here is F2, and this one here is F1. And so now I'm going, and it doesn't really matter where I put it, right? But I'm going to go through the mirror, right, or hit the lens, and then it's got to come out through focus 2. So I line up with focus 2, and it goes up. And then I'm going to aim for focus 1 over here on the other side. So I aim for focus 1, and it comes out parallel. And then I go through the center, and then again, I'm going to use different colors since I can't dash very well. So here's where it ends up. And so here is my image back here. I know it's getting a little squishy. So there's my image, here's my object, and I've got both my foci labeled. And remember, it was these 3 that I extended back. That's it? Yes? All right. So now, the other stuff from chapter 26, I always get the numbers wrong. We have refraction, which is n1 sine theta 1 equals n2 sine theta 2. That's Snell's law. It's due to the differences of n's, which is caused by differences in speeds. F remains the same. Remember, as you go from one medium to the other medium, so as the light goes from air into the water, the F doesn't change. If it goes in with 20 hertz, it goes through at 20 hertz. So since V equals, right, since we know V equals lambda F, right, V equals lambda F, if F doesn't change, but we know the V goes down, we know the lambda goes down, it goes down by a factor of n, which is always a nice thing to know. We know that the V in the medium is C divided by N. So N is like this factor of how much it slows down by, right? And the big N means it goes slower. So the bigger the N, the slower it goes. If you go from a small N to a big N, it goes towards the normal. If you go from a big N to a small N, it goes away from the normal. The more bigger difference you have, the more bending you have. So here are examples. The normal's not drawn in, but there's my normal, and there's my normal. So we can see here that in this case, I can look at this and say, oh, N2 must be less than N1 because it's bending away from the normal. Here we know that N3 must be greater than N1 because it's bending towards the normal, right? So you need to be able to see it, and then how much bending. Now the question is, which one's the biggest N? N1, N2, or N3? So we see that it's hard on this one. I don't know if we could really decide because it bends a little bit on the left. It bends a little bit on the right. I don't know if we could tell, but if they ask which one bent more, then you'd be able to quantitatively, determine which one's the biggest one and then rank them. For critical angle, it must be big N to small n, because remember, otherwise the equation doesn't work because the theta c is equal to the inverse sine of n2 over n1, where theta 2 is 90, and it causes total internal reflection, things like that we saw, like the fiber optics and the waterfall. But it's basically going from water to air. You can't do it from air to water. Brewster's angle, again, it's N2 over N1. It's the tangent of theta B. It causes the light to be polarized parallel to the surface. So we talked about that, about how polarization happens parallel to the surface, but now we know we have an equation for it. And the reflected and the refracted rays are at 90 degrees. So these two rays right here are 90 degrees together. Apparent depth just says that the apparent depth is so that D is equal to N2 over N1. And remember what we said, we know that if it bends away like this one is, then it's going to look like your D prime is going to be less than D. If it went the other way, right, if you were looking from the water up, then you know it'd be the other direction, and so then you know it looked like it was further. So make sure that this ratio always matches what you know conceptually should be happening, just because that's the most common mistake is to put that ratio upside down. For eyes, remember for nearsightedness means you have a long eye. You need a concave lens to fix it, right? Because your eye's too long, so you need to spread that light out. And the image is in front of the retina. For farsighted, that means you have a short eye. It's for convex lenses, or you need to use a convex lens for it. And the image is behind the retina, so you're trying to bring it closer so you can see. So so the big thing is just understanding what the difference is between nearsighted and farsightedness and how you correct. Dispersion is separation of colors to different ends. That's what we see in prisms and in rainbows. That's why blue separates or bends more than red, because it has a higher frequency, so it interacts more with the molecules. And so it has a bigger end, makes it bend more. Problems with lenses can be something like spherical aberration, which means the separation of rays due to the edges are thinner, and then the chromatic aberration is color separation. We don't notice that as much anymore. Used to be a big problem with the TVs, but it's just color separation because all the ends are different. With the different thicknesses, you just end up with more time in the medium. Other equations that you need to know just for this chapter or this whole test is V equals lambda F, F equals 1 over T, and E equals CB. Those are all equations we've had, but I just didn't want you to forget. That's it.